Day 131, Notes Pre-Calculus. Today we're going to fill in information onto a blank unit circle, and we're going to use the data on the from the table on page 419 to help us do that. I'd like to identify the angle measures in degrees and radians, as well as the coordinate of each point that falls on the unit circle. We're going to do that using exact values. Then we're going to come back and answer some questions about this worksheet as well. Ideally, I want you to be comfortable enough with this worksheet, if I were to hand you a blank copy of this, that you should be able to fill it in under 5 minutes. That's how familiar you need to be with this data on this unit circle. So let me just zoom out for a second here so that you can see what we're talking about. This is a unit circle, and its radius is 1, so the length from the center of the circle to its edge is 1. And what you'll notice is that we've got a series of angles that are formed inside the unit circle. So here's an angle, then here's an angle, and so on. We have all of these angles that are created inside the unit circle, and each of these angles forms a measurement that we can identify as a measurement in terms of angles or radians, and they intersect the unit circle at each of these points. So I'd like to have that information written down in this unit circle rather than referring to the table all the time. Now this table only has a handful of measurements available to us, but we're going to use them to get ourselves started here, and then I think we can fill in the rest on our own. So let's go ahead and get started here. If I were to measure the angle from this center point back to itself, the two sides of this angle would be perfectly flat. They'd be laying on top of one another. So if we were to measure that in degrees, that would be exactly 0 degrees. And even if I measured it in radians, that number would be 0 as well. So to start off the circle, we're going to write this as 0 degrees, 0 radians. And the point here, well, it's on the unit circle. It has an x value of 1, but a y value of 0. And that completes this first position. Now for the second position, we've got the angle that's formed here, right there. Now, I told you that we're going to use table 1, or table from page 419, to help us get started here. If we've got 30 degrees, 45 degrees, and 60 degrees as an option to get us started here, I think it's pretty obvious to say that this measurement must then be 30 degrees. It's the smallest of the three that we know. Now, fortunately for us, we can go to the table and find out what that is measurement, or what that is when it's measured in radians. So we have pi divided by 6 radians. And as far as the point goes, now remember, this is forming a right triangle, and this position is the x and y value of this point. X would be the horizontal measurement of that triangle. Y would be the vertical measurement of that triangle. And x is the adjacent side of the triangle's angle, while y is the opposite side. So if you remember from our discussion last week, x would then be represented by the cosine calculation of this angle measure, and y would be represented by the sine calculation of this measure. So cosine is square root 3 over 2. So the x value is square root 3 over 2. And the y value is sine, which is 1/2. That would be the coordinate location of this particular point. Now for the next angle measure, that's this one here. It measures 45 degrees, or pi over 4 radians. Its x value and y value happen to be the same. And that should be somewhat obvious to you because the triangle that's formed here is an isosceles right triangle. This side must be congruent to this side. And those side lengths are square root 2 divided by 2 and square root 2 divided by 2. The next angle measure is one more beyond that. It's a little bit steeper than the others. This happens to be the 60-degree measurement from our table. 60 degrees is also the same as pi divided by 3 radians. And its x value is the cosine value of the angle. Its y value is the sine calculation of that angle. So we have an x value of 1/2 and a y value of square root 3 over 2. So fortunately for us, we only have to remember a handful of numbers. These values keep repeating themselves. This idea of 1/2, square root 3 over 2, and square root 2 over 2 are pretty common in the first set of entries. Now what you'll see here when we encounter the next angle is that we see a right angle formed. And so a right angle in terms of degrees is measured at 90 degrees. In terms of radians, we could call this pi divided by 2. It's half of a pi in radians. Now the coordinate of this point here should be easy enough to find, even though it's not in our table. Well, we have no left or right movement from the origin, so our x value has to be 0, but our y value has to be 1. It's 1 unit away from the x-axis. Now as we start rotating into the second quadrant, we need to recognize that the angle measure still is based upon the positive x-axis. So we're still focused on this side of our angle, and it forms the angle rotated this way. Now what's interesting is that the difference between this angle that's formed and the previous one is still a difference of 30 degrees. It's the same difference that we saw here just a moment ago. Then when I make my next rotation, the difference between that angle and this 90 degrees is 45, and beyond that we go 60 degrees past the 45. So the relationship is still pretty similar to what we've had since the beginning. We just need to identify what the new angle measures are going to be in terms of our initial side along the positive x-axis. So as we rotate, this one is 30 degrees beyond 90, so that makes it 120 degrees. This angle measure here is 45 degrees beyond 90, which is 135 degrees. And this angle measure down here is 60 degrees beyond 90, which makes it 150 degrees. Of course, by the time we reach the x-axis again, we're now looking at a 180 degree angle measurement. Let's use that pattern to fill in the rest of the angle measurements in degrees for the remaining values of this unit circle. 30 degrees beyond 180 is 210. 45 degrees beyond 180 is 225. 60 degrees beyond 180 is 240 degrees, and 90 degrees beyond 180 is 270 degrees. Beyond that, we rotate into 300 degrees, 315 degrees, 330 degrees, and then one full revolution would bring us back 360 degrees. And that completes all of the degree angle measures for the unit circle. Let's consider our radians next. Okay, now you might have noticed that I changed the color of our radian measurements, and I've done that just to make it stand out a little bit more. But you may have also noticed that there seems to be a gap in each of these quadrants. For example, there's a gap right here of a missing angle measure, and there's a gap here of a missing angle measure. Now that we have our degree measurements identified, you might be able to recognize what angle measure would fill that gap. And what it happens to be is an angle measure of 15 degrees. Now 15 degrees or 15 degree increments are fairly common in trigonometry. We could have put them in here on the unit circle, but that would have made things a little bit more crowded. And while it is a popular increment for angle measures, it's just one that's not as popular as 30, 45, 60, or 90. But it is helpful to know that measurement in terms of radians. And I'll go ahead and show that here. This is pi divided by 12 radians. Every 15 degrees, we have 1 pi divided by 12. And so if pi divided by 12 is 15 degrees, then it should make sense that 2 pi divided by 12 is 30 degrees, and 3 pi divided by 12 is 45 degrees. 4 pi divided by 12 is equal to 60 degrees, and so on. And here's where using the increment of pi over 12 is really helpful. The fraction 2 pi over 12 reduces to the fraction 1 pi over 6, which is the result that we found or identified just a moment ago from our table. 3 pi divided by 12 reduces to 1 pi divided by 4. And 4 pi over 12 reduces to 1 pi divided by 3, exactly the same as the information provided to us from the table before. I would suggest using that knowledge to fill in the rest of our radian measures. So I'm going to take the time to clear up all of this side note or side work here. We'll start filling in this information in just a moment. Okay, and we're back, and this is a little bit cleaner now. So remember, we had 1 pi over 12 in this spot, 2 pi over 12, 3 pi over 12, 4, 5, and this would be 6 pi over 12, or reduced to pi over 2. This position would be 7 pi divided by 12, therefore this one is 8 pi divided by 12. Now the fraction 8/12 can be reduced to 2 pi divided by 3. Next would be 9 pi divided by 12. 9 pi divided by 12 reduces to 3/4 pi, or 3 pi divided by 4. And 10 pi divided by 12 reduces to 5 pi over 6. We could fit another angle here, 11 pi over 12, and then lastly 12 pi over 12, 12 pi over 12, and that reduces to just pi by itself. So now we have the first semicircle complete with all pi radian measurements. I'm going to pause the video and ask that you fill in the remaining radian measurements in terms of pi for the lower half of this circle. Again, remember that we're dealing with 13 pi over 12, 14, 15, 16, 17, and 18 pi over 12. Use that as your starting point, as your reference fraction to fill in the rest of the data. Reduce those fractions to lowest terms. And it would be okay to write this as an improper fraction. For example, down here we'll get to 14 pi divided by 12, and I see that that would reduce to 7 pi over 6. 7 pi over 6 would be appropriate for that radian measure. And here we go with the rest of the data. 14 pi over 12, 15 pi over 12, 16 pi over 12. 17 would have been here, 18 pi over 12 reduced here to 3 pi over 2. 19 pi over 12, 20, 21, 22, 23, and finally 24 pi divided by 12 would fill in the rest of this data. So hopefully your answers match mine. If they don't, then please go back and correct them and make sure that you understand how we got to the fractions that we're sitting on right now. The last thing that we'll need to do to fill in this chart here is to fill in the rest of our coordinates around the outer edge or the perimeter or circumference of this circle. Now this too can be filled in without too much effort. What we're going to do is reuse the same numeric values that we have over here in the first quadrant. We just have to decide where they fall in the second quadrant. For example, this position here, this point is reflected over the x-axis from this original point here. It just showed up onto the other side. So in order to identify that as a coordinate, all that I would need to do is change the sign of my x value of the coordinate. Instead of being at a positive 1/2, positive 3 over 2, I'm now at negative 1/2, positive 3 square root 3 over 2. Similarly, at this position, we have negative square root 2 over 2 and square root 2 over 2 for the y value. For the x value in this position, we have negative square root 3 over 2 and positive 1/2. Lastly, this final point is at the point negative 1, 0. Now, when I locate the next points, they're just a reflection over the x-axis. And when I reflect over the x-axis, all I need to do is change the y coordinates sign. So now down here, I have negative square root 3 over 2 and negative 1/2, negative square root 2 over 2, negative square root 2 over 2, and so on. I'm going to pause the video, and you should do the same to fill in the rest of the information for the remaining values of this circle. And there you have it, the rest of the data filled in to this unit circle. Please verify your answers and make sure that you understand where each of these numbers come from. Well, we now have a completed unit circle, and while that took a significant amount of time to fill in this first time, you should be able to memorize these values and the location of each of the angle measures and be able to repeat this exercise again in under 5 minutes. That's your goal, to practice this and be able to complete it in under 5 minutes. Now, to supplement this, it is helpful to understand what our exact radian measures come out to be as far as an approximate or decimal value. So what I'd like for you to do is take each of the radian measures, so pi over 6, pi over 4, pi over 3, pi over 2, and so on. Enter those here. So the next would be pi over 3 and then pi over 2, and use your calculator to approximate what those decimals are going to be equal to. Please have those results ready for tomorrow's class. Now, to finalize the video, I would like to talk about these few questions that we had at the start of our notes today. The smallest radian measure that we saw in this table was 0 radians, and the largest radian measurement was 2 pi radians. The smallest was 0 radians, the largest was 2 pi radians. This is essentially the domain of our sine and cosine functions. What I mean by that is we could select any angle measure between 0 radians and 2 pi radians and enter that as an input value into the function sine or cosine. Now, when we start looking at the x value coordinates, the x values represent the result of our cosine function. And so as a result, we would call that the range of the cosine function, because it's associated with our x value. Now, the smallest x value that we saw on our list was -1, and the largest that we saw was a +1. The range of this cosine function must exist between -1 and +1. And similarly with our y value coordinate, the smallest was -1 and the +1 was the largest. This is what we would call the range of our sine function. The result of any sine function or cosine function will be at its smallest at -1 and largest at +1. There will be no result from any sine or cosine calculation to be smaller than -1 or larger than +1. What that means for us this week is that we must recognize that trigonometric functions typically allow us to find missing side lengths of a right triangle, but our inverse trigonometric functions allow us to find missing angles. An inverse function reverses the domain and range of the original function. This should say of the original function here. So what was prior to this an input value now becomes an output value. What was an output becomes an input. We're going to talk a little bit more about that this week, but I just wanted to plant this seed in your mind just a little bit here, that before long we're going to be reversing our trigonometric functions to find missing angle measures rather than just missing sides. Please let me know if you have any questions over this worksheet tomorrow in class. I'll be happy to discuss it with you then.